Welcome! Today, we're going to demystify a key rule in algebra that you'll see all over the place. Rationalizing the denominator. It's a must-know for simplifying expressions and tackling more complex equations down the line.
Okay, let's dive right in with a question. You see this fraction, 1 over the square root of 2. Now, it's a perfectly good number, right? But in the world of algebra, it's actually not considered simplified. So, why not? What's the deal?
Well, this brings us to a really fundamental convention in math. Think of it less like a hard and fast law of the universe and more like a rule of etiquette, or maybe even grammar. It's just the standard, accepted way to write our final answers so that they're consistent for everyone.
So what do we actually mean when we say rationalizing? It's pretty simple, really. All we're doing is making the denominator, the bottom part of the fraction, a rational number. The big rule of simplification is no radicals in the denominator. Our whole goal is to move that square root out of the basement, so to speak.
And just to be super clear, this process isn't about changing the actual value of the fraction at all. It's all about proper formatting. You know how in English class you're told not to end a sentence with a preposition? It's kind of like that. You just don't leave a radical in the denominator of a final answer.
All right, let's get into our first method and see how this works in the most common scenario you're going to face, when the denominator is just a single, simple, radical term. In math speak, we call that a monomial.
The trick here is actually pretty genius in its simplicity. We just multiply the entire fraction by a very clever form of the number 1. We take the radical from the bottom, put it over itself, and multiply. Since anything divided by itself is 1, we aren't changing the fraction's value one bit. We're just changing how it looks.
Okay, let's walk through an example together. Let's say we have 5 over the square root of 3. The radical we need to get rid of is root 3. So we multiply the whole thing by root 3 over root 3. The top becomes 5 times root 3, and the bottom, well, root 3 times root 3 is just 3. And there you have it. Our final answer is 5 root 3 over 3. No more radical on the bottom. Mission accomplished.
Now, this second example adds a really crucial final step, so pay attention. We've got 6 over 3 root 2. Here, we only care about the radical part. That's the root 2. So we multiply by root 2 over root 2. That gives us 6 root 2 on top. On the bottom, we have 3 times root 2 times root 2, which is just 3 times 2, or 6. But wait, we're not done yet. Look at that. The 6's on the top and bottom cancel each other out, leaving us with a beautifully simple final answer, the square root of 2. So remember, always check if you can reduce your fraction at the end.
So, that was the simple case. But what happens when the denominator is a bit more complex? Like, what if it's a radical that's being added to or subtracted from another number? For that, we need a pro move.
Here's what I mean. On the left, you've got that monomial denominator we just dealt with. But on the right, we have a binomial, 2 plus the square root of 5. Now, if we just tried multiplying by root 5 like we did before, we'd have to distribute it, and we'd still end up with a radical in the denominator. That doesn't work. We need a different tool for the job.
And that tool, our secret weapon, is something called the conjugate. It's a simple idea, but it's incredibly powerful. All you do is take the binomial from the denominator and just flip the sign in the middle. So the conjugate of 2 plus root 5 is, you guessed it, 2 minus root 5. When you multiply these together, it brilliantly cancels out the radical, all thanks to a cool pattern you might remember called the difference of squares.
Let's watch the conjugate in action. To rationalize 3 over 2 plus root 5, we're going to multiply the top and the bottom by its conjugate, which is 2 minus root 5. On top, we just distribute the 3 to get 6 minus 3 root 5. Now for the magic on the bottom. The difference of squares gives us 2 squared minus root 5 squared, which is just 4 minus 5, or negative 1. Dividing our numerator by negative 1 just flips the signs, giving us our final answer, negative 6 plus 3 root 5. See, no radical on the bottom.
Okay. Now let's quickly cover the most common mistakes people make, because honestly, knowing what not to do is just as important as knowing what to do.
So, you might be wondering, why is the conjugate so important? Why can't I just use that first method and multiply the denominator by itself? Well, let's take a look at what happens if you do.
If you multiply 2 plus root 5 by itself, you have to FOIL it out, and you get these cross terms in the middle that still have a radical in them. The middle terms don't cancel, and you're left with a denominator that's actually more complicated and still has a square root. You're basically right back where you started. You haven't solved the problem at all.
So if you only remember 2 things, let it be these. First, for those two-term binomials, you always have to use the conjugate to make sure those pesky radicals cancel out. And second, no matter which method you use, always give your final answer one last look to see if it can be reduced.
At this point, I know what you might be asking. Okay, but when am I ever actually going to use this? Believe it or not, this isn't just some random classroom exercise.
This is literally the standard way to present answers in tons of technical fields. When physicists or engineers are working with an exact value that involves a radical, they always use the rationalized form. It's like a universal language for presenting calculations and data precisely.
And here's a perfect example that illustrates the point. In trigonometry, the sine of a 45-degree angle is technically 1 over the square root of 2, but you will never, ever see it written that way in a textbook or a scientific paper. It's always presented in its rationalized form, the square root of 2 over 2. It just goes to show how essential this standardized notation is.
So there you have it. You now have a key skill for simplifying expressions. Mastering this really does open the door to solving more advanced equations. By cleaning up your fractions this way, you're getting yourself ready to tackle much more complex problems in algebra and beyond. So the only question is, what will you simplify next?